6.2, we're finally at trig proofs. We're finally at trig proofs. I wait all year long for this section, and now we're finally here. Okay, so I know you read this yesterday, but here's the quote that I like to compare trig proofs to. It's from W.S. England, and it says, "Mathematics, or for this case, you could put trig proofs, it's not a careful march down a well-cleared highway, but rather it's a journey into a strange wilderness where the explorers often get lost, right? Rigor should be a signal to the historian that the maps have been made and the real explorers have gone elsewhere." You're going to be real explorers. We're going to have to, with our mathematical machetes, create our own path through some sticky things, okay? Let's start with example 1. The instructions are simple. It says to prove, look at what I'm doing. I think I'm using a highlighter. Stupid me. Prove the following identity, okay? So here's the good thing. You're going to know in advance that something is, in fact, an identity. When you come across something like this in the real world that's an equation, you don't know if it's a conditional equation. You don't know if it's true for some values of x. You don't know if it's true for one value of x. You don't know if it's true for all values of x. You don't know. You're going to know in advance that it's true for all values of x. That's a little helpful. You're going to know that these things are identities. All right, so here's how we start the proof. We're going to draw a line down the equal sign. Okay, this is to keep us from cross-contaminating. Like, I cannot subtract 1 from both sides. I can't multiply both sides by 2. I can't do what I normally do in a conditional equation. I have to work each side separately, okay, keeping them equivalent the whole time, and I just keep working down until the left side and the right side look the same. When they, bless you, look the same, we're done, okay? So, step 1, after you draw the line down the middle, is decide which side to start on. Okay, because you could really work on either side. Both sides would work. But in general, we mentioned this the other day, it's easier to tear something down than to build it up. Yes, yes? So you want to start on the side that has more information, the side that looks more complicated. That's your first strategy. Which side to you looks more complicated? The left. Okay, now I'm going to agree with you for 2 reasons. The left side has 2 trig functions, whereas the right side only has 1 trig function. But another reason that's almost more important is the left side has higher powers than the right-hand side. You can think of a higher power as being a denser nucleus. There's more information there to unpack. Okay, so here's what you have to tell yourself then. I need to get the left side manipulated until it looks like 1 minus 2 cosine squared of x. So what can we do to start? Well, we can do some algebraic techniques, right? We can combine like terms. We can divide out common factors. We can expand something by multiplying it out. We can factor something, okay? And we can also replace something with an identity. That's the powerful thing, and we have to know when to do that. For example, I could right out of the gate say sine to the 4th of x is 1 over cosecant to the 4th of x. Would that be okay? Is that true? It's true, okay? But is it going to be helpful in this case? No, because whatever side you start on, if we start on this side, guess what the other side becomes? It becomes your target. Yeah, you need that other side to be accomplished. So it's a little bit easier, I think, than what we did in the previous section, where we were just vaguely simplifying down to a power of a trig function. We didn't know exactly what we were supposed to end up with. Here we know exactly what we're supposed to end up with. So going into cosecant land would be kind of a step in the wrong direction, I think, because the right side just has cosine squared. So I'm not going to go that route. But here's what I'm going to do. Remember I said 4 is a denser nucleus than 2. I need to somehow tear down the power of 4 into a power of 2, which means I'm going to have to do it by doing what? There, who said that? F it. We're going to factor it. Yeah, we're going to factor it. Okay? This is actually a difference of 2 perfect squares. Okay? If you had x squared minus y squared, that's equal to x minus y times x plus y. But it works for any even powers. You can have x to the 4th minus y to the 4th, and it simplifies down to x squared minus y squared into x squared plus y squared. It doesn't always have to be just the boring powers of 2. As long as it's any even exponent, you can have x to the 4th minus y to the 6th, and it would be a difference of 2 perfect squares. All you got to do is take half the exponent when you factor it. One's plus, one's minus. Okay? So what does this factor into? It factors into sine squared of x minus cosine squared of x times sine squared of x plus cosine squared of x. You want to start sufficiently to the left so that it all fits in there to the left of the line. Is what just one? Do you see something already? Like we just literally factored it and you're already seeing something appear. Yes, this is because, Peyton, you know your identities. Thank you. And he's what? And he's thinking. And so are you. If you don't have your identities memorized, you are going to be dead in the water because you have no idea that you're staring at something that's equal to something else. Okay? But if you do know your identities, you're aware of them, you're like, sine squared plus cosine squared, that's just what? That's just 1. So this turns into sine squared of x minus cosine squared of x times 1. Now, here's the thing with trig proofs that we don't have to do that you might have had to do with geometric proofs. You don't have to write the reason off to the side. Like you don't have to say factor here, and then you don't have to say pop a PID. Remember, you had to do that with geometry. You had to write the postulate of the theorem. You don't have to do that. The work itself is algebraic, and it's understood. Now, I do have to call sine squared plus cosine squared a 1. I do need to be able to see the algebraic substitution, okay? So when in doubt, don't leave it out. When in doubt, don't leave it out. Now, what's anything times 1? Itself. So now I could say sine squared minus cosine squared. And now I've accomplished something. I've taken it from a power of 4, and I'm taking it down to a power of 2, which is what I want. So now the other side being your target, now you ask yourself, okay, now that the power of cosine is squared, I want the cosine to be squared. But on the other side, there is no sine squared, is there? There's no sine squared. So I need to think about this. This is your thought process. How do I get rid of a sine squared completely and possibly, notice there's a 2 cosine squared over there, and possibly put it in terms of a cosine squared? There you go. Pop a PID again. So in the substitution, this is minus cosine squared. Just bring it down. Sine squared is 1 minus cosine squared of x. And there's your next substitution. Sine squared of x is 1 minus cosine squared of x. Now the parentheses are only there to show the substitution. There's really nothing to distribute, is there? So we could drop the parentheses, and you get minus cosine squared minus cosine squared. What that becomes what? 2 cosine squared. They're like terms. Does the left side look like the right side? It sure does. So guess what? Did we finish the proof? Yeah. So you can sign off however you want. Dirty diaper. Yeah. Or QED. You can put QED. You could sign your name. You could put Bazinga if you watch that show. Chat. Yeah. Whatever you want. Just keep it clean. And by clean, I mean not profane. Dirty diapers are not very clean. Right? Whatever you want. I used to sign my name until I came up with dirty diaper. I just like it. Dirty diaper. Any questions on this? So every problem is going to present its own little piece of strategy, a little tidbit of wisdom that's going to help us when we do other problems. What's this one? Not only start on the most challenging side, or the side that has the higher power, but look to factor. There's the strategy from here. Look to factor. All right? So we sum that up right here. We're going to point out the algebraic morals of each example as we encounter them. This one was factoring. Look for common factors. Look for difference of squares. Look for perfect square trinomials. Look for difference in sum of 2 cubes. All of the factoring stuff that we've had in the past, look for it. We can factor with trig. It doesn't have to just be plain old boring x's. All right, questions on that? That's what a proof looks like. Any comments on that one? Okay, let's go to the next one. Letter 2. This is an identity. It's true. It is absolutely true that tangent of x plus cotangent of x will equal secant of the same angle times cosecant of that angle for all values in the domain. It doesn't work for all real numbers, but for every value that does work on the left side and works on the right side, that means it's in the domain, you're going to get the same number. Okay, there's infinitely many solutions. Step 1, draw your line down the middle. That's always step 1. That's an easy step to do, right? Draw the line down the middle. That keeps you from cross-contaminating. Now we pick the side that is more information. What do you say? Left or right? Why do you say the right? It's multiplication, right? Good. Okay, it's multiplication. The left side is addition. Now, here's what I would tell you. I would actually start on the left side. Okay? Well, not necessarily because they're weirder trig functions. They both have two trig functions. But here's why I would start on the left side. It's easier to combine fractions than to split them up. That's a fact. It's easier to combine fractions than to split them up. Okay, so here's what I mean. If you have 1 over a plus 1 over b, that's 1 over ab. Okay, 1 over ab, or 1 plus 1. Sorry, it's 1 plus 1 over ab, which is 2 over ab. Okay, all you need is a common denominator. You need a common denominator. And it's easy to find a common denominator and to combine two things. It's a lot harder to, it's not equal to 2ab. What am I thinking? Okay, but I can get a common denominator by multiplying this one by b over b and multiplying this one by a over a, and I get b plus a over ab. That's what I meant. Sorry, I was going too fast. Sorry, I've already been teaching calculus for a whole hour already this morning. My brain's a little wired. I had so much coffee this morning. I got up an extra hour early, and I had so much extra coffee than my usual pop. Well, I usually get up at 4:30, but I got up at 4 this morning because I couldn't sleep. I was having a dream, and then I woke up, and I couldn't go back to sleep to continue my dream. So I was just like, it's 30 minutes early. I popped out of bed. And so I had 30 extra minutes of coffee. Just because it's quiet, and I like the quiet. I can get stuff done in the morning. I can watch Sports Center in the peace and quiet. Yeah, I get stuff done in the morning. I listen to music. Like today's Friday, all the albums came out, so I listen to music.
I don't know if it's like an insult. That's what my grandparents do too.
Yeah. When I was 18, I was going to bed at 4 in the morning. Now I'm 50, I'm getting up at 4 in the morning.
They like to sit on their porch and drink their
Absolutely. I love it. I sit on my back deck with my dogs. Absolutely. Or I sit on my front deck with my dogs. Yeah, it's just me in the morning, my coffee and my dogs, and just the peace and quiet. Well, this morning it was music in my ear. Sometimes it's Sports Center on the television, but I get like 2 whole hours to myself in the morning, and I love the morning. I'm a morning person. I've always been. Yeah. So anyway, you get b plus a over ab. It's really hard to go this way. It's really hard to split it up and go that way. That's hard, but it's easy to go from left to right. Okay. So that's why we start on the left. So that's another little bit of wisdom here, right? Start on the side that has more terms. Start on the side that has more terms. All right, now, I said it's easier to combine two fractions when you have a common denominator. Do you even have fractions here?
Not yet.
No, not yet. So that's another strategy. Make fractions. Let's use the ratio and the reciprocal identities if we need to. Do you want to call tangent 1 over cotangent? Or do you want to put it in terms of sine and cosine right away? Okay, there's two options, right? This is where you have the option. Sine over cosine and 1 over cotangent. I'll call it sine of x over cosine x. That's what y'all said. Plus cotangent is cosine x over sine of x. Okay? There's the first thing. Now, on this line, you can go ahead and do this. I need a common denominator. It's sine times cosine. So this one I multiply by sine times sine, and this one I multiply by cosine over cosine. I just need to be able to see it. And now my common denominator is sine x cosine x, and I'm left with sine squared plus cosine squared. So I did two things on line 1. I wrote them in terms of the ratio identities, and then I got a common denominator, and I showed that. Sine over sine, cosine over cosine. Okay, now I combine the numerators all over the common denominator, and now we reassess. How's it looking like the right side? The right side is my target. Is it looking good? It's looking good in the sense that it's now a single term, yes? The right side is a single term, so I've got my single term. All right, now we're staring at it, and what's happening? I see Papa Pitt again. He's all over the place. That's 1, so I get 1 over sine of x cosine x. Now, it is easy to split up fractions when it's a single term. If you have multiple terms in the top, like sine plus cosine or b plus a, it's hard. This is the same now because they're multiplied as 1 over sine of x times 1 over cosine x. Would you agree? Because when you multiply straight across, 1 times 1 is 1. Now, what's another name for 1 over sine of x? Cosecant of x. What's another name for 1 over cosine? Secant of x. Is that what I have on the right-hand side?
Well, pretty much.
Wow. Should we stop here then?
We just flip them.
We don't stop here is what you mean. You don't stop until the left side looks exactly like the right side. If there's a reason for doing something, you want to show that step. This would be the commutative property of multiplication. A times B is the same as B times A. So that's secant now times cosecant, and that would be commutative property of multiplication. Now can we stop?
Yeah.
Now you can stop. They have to look exactly the same. And when in doubt, what do? When in doubt, leave out a step, or when in doubt, don't leave it out? Don't leave it out. Your process is the product. Your process is what I'm actually grading. I'm going step by step through each of your lines, and I have to follow with integrity all the way through to the end. Okay, so now we can put dirty diapers. I'm just going to put DD, dirty diapers. Dirty diapers. All right. All right, so let's go ahead. When all else fails, get everything in terms of sine and cosine. That's the strategy. We didn't even really think about it. Y'all didn't want to do 1 over cotangent and 1 over tangent. Y'all wanted to put everything in terms of sine and cosine right away. Guess what? That's another strategy. You can get everything in terms of sine and cosine. That strategy works at any time, right? We saw yesterday when we did the simplifying one that if we went in terms of sine and cosine too early, it made the problem a lot longer. Whereas if we would have kept it in terms of tangent, cotangent, it was a very quick thing on the quiz yesterday. So just, I would wait until everything else fails. If it's the only insight you have is to put everything in terms of sine and cosine, go for it right away. And of course, combine terms by getting a common denominator. Make fractions. Make fractions, get a common denominator. Start on the side that has more terms. There's a lot that we've gotten out of this one little problem, right? So we've got a couple under our belt. Factor when you can. Start with more terms, make fractions, get a common denominator. How y'all feeling about these proofs so far? So far, so good? You think you could do 1 or 2 on your own? Okay, well, that's what the worksheet's for. Every problem that we have here is going to have a little bit more to learn, and I don't want to set you loose on one of these examples because you're going to get stuck maybe because you haven't seen the strategy before. But once I make you aware of the strategy, now you're like, oh, yeah, we could just do the same thing here that we did in that problem 2 years ago, whatever. All right, step 1, draw a line down the middle. Step 2, start on the side that has more information. Which side do you want to start on based on the previous problem? The left side. It's got more terms, doesn't it? It's got fractions and it has more terms. So I would start on this side. Let's start on the left-hand side. All right, what do you want to do first?
Square root. Or not square. Can you square them?
Here's what you can't do. Can you just square the left side? Or can you just square the denominator? Is that legal? When you square something, do you change its value? Yeah, you can't just do that. You can square both sides of the equation if you're solving, but we're not solving, we're proving. So we can't square both sides of the equation. Squaring is off limits. It changes the value. What did we do up here? We had 2 fractions. We got them into 1 fraction by getting a what? A common denominator. Would that be a viable first step here then? Yeah. So I'm going to go down to the next line because there's no room here. The common denominator for secant x minus 1 and secant x plus 1 is their product, right? When in doubt, take the product of the two and you have a common denominator. So I'm going to do 1 over secant of x minus 1, and I'm going to multiply it by secant of x plus 1 over secant of x plus 1. And then I'm going to say plus 1 over secant of x plus 1. I'm going to multiply that by secant x minus 1 over secant x minus 1. Now this is kind of 2 strategies in one. The first strategy is combine terms by getting a common denominator. The second strategy is how are secant x minus 1 and secant x plus 1 related? They're what's of each other? You tell me.
I know. No. The square.
They're conjugates of each other. We already had this strategy the other day when we were simplifying. I said when you have a 1 minus cosine of x multiplied by 1 plus cosine over 1 plus cosine, that's the conjugate over the conjugate. And anytime you multiply by the conjugate over conjugate, you get a difference of squares. And a difference of squares will set up a Pythagorean substitution. Do you remember that from the other day? Okay, so that's two strategies in one. We're just getting a common denominator. They happen to be conjugates of each other. So let's go ahead and see what we get on the next line. We're going to get secant x plus 1 times secant x minus 1. That's our common denominator. And in the top, if I multiply across, I get secant x plus 1 plus secant of x minus 1. Are we making progress? Look at your target on the right-hand side. How are we doing? We're good. I have a single term now, don't I? It still looks a lot hairier than the one on the right, but at least I have a single term. All right, now what? What can I do? Let's look at the numerator first. Is there anything I can do in the numerator? I can cancel out the ones. Now, if you're going to do that, make sure that I can still see that there was a 1 and a minus 1 there. Don't just scratch it out. You can cross them out if you want, but I need to see what's underneath the cross out. And what about secant plus secant? Combine them to get what? 2 secant of x. Okay, now look at the right-hand side. How am I doing? I'm doing great. Look, I needed a 2, and I have a 2. I'm almost halfway there. I got the 2. Woo! Making progress. All right, in the bottom now, what can I do with secant plus 1, secant minus 1? Combine them, multiply them out, right? You're going to get what? Secant squared minus 1. You get a difference of squares. The middle terms cancel out. You don't have to show the middle terms. You can just say, oh, I know they cancel. They're conjugates. So it's the first one squared minus the last one squared. Okay, cool. Now, when you see secant squared minus 1, the bell should go off in your head. When you see a squared trig function, especially in the presence of the number 1, you should be thinking PIDs. Now, I know that you probably don't have this one memorized and can manipulate in your head. Maybe you do. But you off to the side could write it out. I know that 1 plus tangent squared of x is equal to what? Secant squared of x. So if I just bring the 1 across, I get secant squared of x minus 1 equals what? Can I make that substitution? I absolutely can. Yeah, so I get 2 secant of x all over tangent squared of x. Now what that did is it got rid of the 2 term dude in the denominator. And now you look at your right-hand side and you're like, I'm making great progress. I'm making great progress. But I still only have the 2 in the right place. What can I do now? Here's what the proof is left. All I have left to show is that secant divided by tangent squared is cotangent times cosecant. That's all I have left to show, right? What? Did y'all hear that? We can do that. As long as we have factors, we did this the other day on the quiz, yesterday on the quiz, I could bring a tangent squared from the bottom to the top and call it what? Cotangent squared. I could bring a secant from the top to the bottom and call it cosine if I want. As long as it's a factor, it's being multiplied, you can bring any trig function from one side of the fraction to the other as long as you call it its reciprocal. So let's try that. 2 secant of x times cotangent squared of x. Now, why did you even think to do that, Brady? There's 2 reasons. Very good. Notice that I needed, as Brady said, a cotangent. I needed a cotangent factor, and now I got 2 of them. I also needed to get rid of the fraction, didn't I? That got rid of the fraction. But I have an extra cotangent factor. So really now what I need to show is that secant times cotangent, the other cotangent, secant times cotangent, I need to show that's equal to what? Cosecant. How do I do that? Oh, do you want to go back to plus 1? No, the right side doesn't have plus 1. I want to stay like this. So here's what I'm saying. Let's go ahead and start a new column. Okay, here's our new column, right? Here's the double line to separate it. I have 2 secant of x, I forgot the x, don't forget the x, go back and put it if you forget it, times cotangent squared of x. Let me go ahead and rearrange these factors. This is called the associative property of multiplication. Let's write it as 2 cotangent of x times secant of x cotangent of x. Are you okay with that? What I did is I put the 2 cotangent of x in front, because that's what I want, and then I just put the other cotangent and the other secant together. So really now all I have left to show is that secant of x times cotangent of x is equal to cosecant of x. That's all I have left to show. The 2 cotangent of x is in place. Any ideas how we could do that? Any strategies that we've already had or any insight? What do you mean fractions?
Like secant 1 over cosine and cotangent cosine of sine.
So put everything in terms of what? Yeah, if you're trying to simplify a quotient down to something and you're not sure what it is, put it in terms of sine and cosine. That's the very basic part of it. So here's what we're going to do. We're going to leave 2 cotangent of x alone. Secant is 1 over cosine of x. Cotangent is cosine x over sine of x. And now if I work down, I just keep the 2 cotangent of x intact. What happens with the cosines? They divide out. And what am I left with? 1 over sine. And what's another name for 1 over sine? Is that what I wanted? Dirty diapers. I'm going to put FTH. Factor the heck out of it. No. Fear the horn. Fear the horn. Yes. Where did it go? I used the associative property of multiplication. I just split it up. I put 1 cotangent factor in the front with the 2 because that's what I needed over here. See, this was my target. So I put 1 cotangent behind the 2, and I left the other cotangent at the back where it was. We could do that with addition, and we could do that with multiplication, yes? Yeah. Long Creek already has their motto. Do you know their motto? Breathe the fire. That's their new motto. They go around saying, breathe the fire, baby. And we have all kinds, right? We have fear the horn. Unicorn pride is justified. That's still my favorite. We have it's a great day to have a great day. We have it's a great day to be a unicorn. We have NB is the place to be. We have it's a great day to have a great day if you're having a great day. We have that one. That's my favorite. Unicorn pride is justified. That's my favorite. I like things that rhyme. But fear the horn is my second favorite. I say that when I do the parades at the end. I say, fear the horn, baby. I almost want to say, fear the freaking horn. But you know, instead of frickin', I almost slip out the other word. Fear the factor horn, baby. But I have to bite my tongue. Fear the factor horn. What if I just said fear the effing horn? You think the student body would get it? Oh, he means factor. Yeah. I should probably refrain from doing that if I want to keep teaching. Okay. There you go. That was a great problem. Did it take more than one column of work? Yeah. Are some of them going to be a little longer than others? Yes. Yes.
If you need to do an extra column, you just put it on the other side of the.
Yes. Uh-huh. Yeah. Now, notice it says, adding to our awesome list of algebraic strategies, eliminate any complex fractions. We actually did it a little bit differently than I'm used to doing it. Some people in the past wanted to put secant right away in terms of cosine, and that would be 1 over cosine, and then you can get rid of the complex fraction. So I'm going to add that to our list right here. Whenever you create a complex fraction, and we saw that yesterday on the quiz or in the notes, your next step is to eliminate the complex fraction by either doing stay, change, flip. You can do stay, change, flip, SCF, or lick 'em over lick 'em. Okay, stay, change, flip, or lick 'em over lick 'em. But that's your next algebraic step. Stay, change, flip, or lick 'em over lick 'em. All right. Any comments or questions on example 3? Whoa! Now, any questions on 3? You see what that goober wore on the left? You see what he wore in front of the whole district? We had our back to school bash at Unicorn Stadium, and all the teachers from K through 12 and all the principals from K through 12 were in the stands. And Reno and I were the MCs for the whole event, and we were going as the summer blockbuster hits. He was going as Oppenheimer. Can you see? Can you tell that's Oppenheimer? And I was Barbie. Yeah, yeah. Well, I was. We called him. He called me Barpy. Yeah, Barpy is what Reno kept calling me. So I was officially Barpy, and he was Renoheimer. Yeah. You know, I don't really read my emails. 49,874. Yeah, if you want to reach me, you kind of have to talk to my face. That's the best way to get a hold of me. Yeah, I didn't think anyone would ever see that. I'm kind of embarrassed by that. Not a big email guy. If it's important enough, you can tell me to my face, right? Or text message me, but you don't know my cell phone number. Or do you? Prove the following identity. Notice we switched to a variable of t instead of variable of x. Is that okay? Yeah, that's fine. All right. So I draw a line down the middle, and that discourages me from multiplying both sides by something or adding something to both sides. I got to work on each side independently. Okay. Which side do you want to start on, the left or the right? They both look equally complicated, huh? Why the left? All the other ones are on the left. Well, I mean, you're training. That makes sense. Is there a PID? Is there a PID anywhere? They're not squared. No. Now here's just a little fact. Okay? It's easier to split up numerators. It's easier to split up numerators than denominators. That's just a fact. Okay? So if you have A plus B all over C, that's the same as A over C plus B over C. You can't split up denominators. If you have A over B plus C, that is not A over B plus A over C. So, with that, you might lean towards the what side? You might lean towards the right side. Let's see what that would entail. If I split up the numerators, that would be 1 over cosine of t plus sine over cosine of t. So there's nothing illegal about that. That's totally legal. And then you could say, 1 over cosine of t is secant of t, and sine over cosine is tangent of t. So you've gotten that far on the right-hand side, but what's your target? Your target is the left-hand side. Are you getting any closer to your target? No. You actually look like you're getting farther away from your target. You have split it up into 2 terms, whereas the target is still 1 term, and you put it in terms of secant and tangent, which the left side is in terms of cosine and cosine. So although that is a possibility, it's probably not the way we want to go. Okay? So I'm going to take this work right here, which is not incorrect, and I'm just going to move it and shrink it and put it over here. I'm just going to file that away on a shelf that says, yeah, maybe not now. You sure? Which side are you talking about? The left side or the right side now? Which side? Okay, you want to multiply by cosine over cosine. What inspired you to do that? Ah, okay. Here's the strategy, and I like what you did there. You're thinking actually a couple of steps ahead. Here's what I thought you were going to say. The left side has a factor of cosine in the numerator, doesn't it? Why not go ahead and create what we need? Let's create what we need. That's a strategy. If we need a cosine factor in the top on the right, let's go ahead and introduce a factor of cosine on the right. Now, how do I introduce it legally? I got to multiply by a cosine in the bottom as well. Okay, so that's the catch. So let's do that. That would give me a cosine of t in the top. I don't want to distribute, do I? I do not want to distribute in the top because I want the cosine visible right there. Okay? Now I've got the cosine that I need. Now on the bottom, what's cosine times cosine? Cosine squared of t. Here's where Brady was thinking. Cosine squared of t is equal to what? It's equal to 1 minus sine squared of t. And what's unique about 1 minus sine squared of t? It's a what? Is it factorable?
Yeah.
It's a difference of what? It's a difference of squares. So let's leave the top alone. We know that a difference of squares factors into the product of two what you gets? Conjugates. So I could say it's 1 minus sine of t times 1 plus sine of t. And now you're going, ooh, 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 ooh. Because what divides out? 1 plus sine of t divides out. And we're left with cosine of t all over 1 minus sine of t. Is that what we have on the left-hand side? Fear the horn. I like FTH. It's easy. Fear the horn. We did it. Good insight, Brady. Create what you need. You were looking more at setting up the denominator 2 steps ahead. You play chess? Oh, you should, because you were thinking like a chess player there, several moves ahead. I was thinking more just like checkers. Well, we need a cosine. Let's put a cosine. You were thinking we need a 1 minus sine. So if I multiply by cosine, that gives me cosine squared, which is 1 minus sine squared, which will be 1 minus sine times 1 plus sine. Yeah, and that'll give us the 1 minus sine that we need. That's what you were thinking.
Yeah.
Crazy. Now, that's the strategy. Create what you need. Now, watch this. Let's do it from the other side. Because the other side is going to be introducing another strategy that we've already talked about. If you see 1 plus or minus a trig function, if you see 1 plus or minus a trig function, or a trig function plus or minus 1, a good strategy to get the ball rolling is to multiply by the conjugate over the conjugate. That's a good strategy. So I see 1 minus sign. I'm going to multiply by 1 plus sign and multiply by 1 plus sign. Now, you could also think about it as creating what we need, because by multiplying by 1 plus sign in the numerator, isn't that what we need in the numerator on the other side? Yeah, so in a sense, it's also creating what we need, but we're doing it with the conjugate over the conjugate. Now look what we have. In the top, we don't distribute. We just keep it as 1 plus sine of t because we need that exposed times cosine of t. And now, instead of having to factor, we're multiplying. What's 1 plus sine of t times 1 minus sine of t? 1 minus sine of t what? Squared. And now, instead of doing the substitution the other way, we're doing it in reverse. What's another name for 1 minus sine of squared of t? Cosine squared, right? That's cosine squared of t. And what happens with one of the cosines now? Oh, yeah, it's positive. Thank you. What happens with one of the cosines? One of the cosines divides out now, and we're left with what? 1 plus sine of t over cosine of t. And that gives us the right-hand side. So create what you need. That's the strategy here. And or look for opportunities to multiply by the conjugate over the conjugate. How do you feel about that? Either way, which way is correct? Starting on the left side or starting on the right side? They're both correct. Yeah, they're both correct. Okay, so multiply by a clever form of 1, conjugate over conjugate, to set up a difference of squares that leads to Pythagorean substitution, or do that in reverse. Expand the conjugates, leaving the other side factored, and let's add this strategy right here. Create what you need. Create what you need by multiplying by a clever form of 1. Clever form of 1 all over a clever form of 1. Hi, Cheyenne. I'm just saying hi to Cheyenne in case she's watching this video in the future. All right, example 5. Prove the following identity. Prove the following identity. Sure thing. We're getting pros at this. They start looking a little bit more interesting, though, as you go through more and more. They're getting a little more challenging. All right, what side do you want to start on? Left side? What would you do on the left side, Brady?
Multiply by 1 plus cosine.
Not 1 plus cosine. If you're going to do the strategy that we just talked about, you would multiply by the conjugate of 1 plus cosine, which is 1 minus cosine. Now, let's think a little bit like a chess player. The whole reason I would multiply by the conjugate is to set up a difference of squares. That's going to give me 1 minus cosine squared. 1 minus cosine squared, then, by Papa Pig, could become a sine squared. And now it would be a factor of sine squared in the bottom. A factor of sine squared in the bottom is the same as a factor of what in the top? Cosecant squared. Is that what we want? Yeah. So there you go. That looks like that's going to bear some fruit. So let's continue on then. We're going to leave the top factored for now. Secant of theta times 1 minus cosine of theta. We'll leave it factored. And we get 1 minus cosine squared of theta. That gives us secant of theta times 1 minus cosine of theta. We're leaving it factored. All over sine squared of theta. And now I could bring the sine squared from the bottom to the top. So that becomes cosecant squared of theta times secant of theta times 1 minus cosine of theta. All right, now I compare it to the right-hand side, and I'm like, yeah, buddy, I got the cosecant squared of theta. But look what I still need to show. I still need to show that the two pieces that are not highlighted are equal to each other. What could I do? Is there something still? Could I distribute the secant? Will that work? Is that something I could do? Let's try it. I mean, it's factored. Let's try multiplying it. What's secant of theta times 1? Secant of theta. And what's secant of theta times cosine of theta? Why is it 1, Brady? You're right, because they're what's of each other? Not inverses. It rhymes with reciprocal. Reciprocal. What's anything times its reciprocal? 1. Anything times its reciprocal is 1. Secant times cosine is 1. Tangent times cotangent is 1. Sine times cosine is 1. Now, if you didn't know that, you could write secant as 1 over cosine and then see that they divide out. Or you can write cosine as 1 over secant and see that they divide out. You also look at your target and you're like, man, the only thing that I would need for it to be is what? I'm hoping that it's a what? A 1, because that's all I need to match up the left side to the right side. Did we match up the left side to the right side? We did. Breathe the fire. No, we're unicorns. Yeah. Unicorn pride is justified. Upage. Uppage. 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 Uppage for short. Oh. Yeah, uppage. God. If you touch the screen with 2 fingers, it does undo. I accidentally keep doing that. What's that? Are you kidding me? 3 fingers is redo? Oh, yeah. How about that? I wonder what 4 fingers does. How about 5 fingers? 6 fingers? What if you put 10 fingers and 2 toes? I didn't know that. Thank you. I learned something new. Yeah, computer restarts. No, it probably is like, get your stinking filthy toes off me. That's what it does. All right, so here's yet another strategy. Do any quote-unquote obvious math, such as distributing, combining like terms, etc. What was the obvious math to do here? Distributing. Okay, distributing. That was the new strategy. All right, we got time for one more. No? You want to stop there? Is that enough digesting for today? Okay, we got through example 5. I'm ready to do some more, baby. You got to like proofs, right? You got to admit proofs. No, come on, come on. You got to have the right mentality going into your homework. That's PHI. That's the variable phi. Yeah. One of our strategies on the next equation is change all the variables to x if you don't like the variable I give you. Okay? All right, y'all have a great weekend.